Okay, so in the last class, we discussed how to discretize the forward difference, backward difference, and central difference. Okay, now let us have a general method. So, general method. Now, in general, uh, we wish, say, for example, say we want del t del x. This has to be evaluated at I, say, for example. Then in that case, we approximate this. We want an approximation of this as, say, C naught T I plus C1 T I plus 1 plus C minus 1 T I minus 1. Okay. You can add more terms. Let us say this is an expression. Now, 1 T I plus C1 delta x delta t delta x I plus C1 delta x square 2 factorial delta 2 delta x2. Similarly, you can write C minus 1 T I minus 1 equals to C minus 1. C minus 1 is a term, okay, just a constant coefficient, naming them as C1 or C minus. This is subscript Ti plus C minus 1 delta x delta t delta x plus C minus 1 delta x square 2 factorial. Now from zeroth order term, zeroth order term, zeroth term, you can write C naught plus C1 plus C minus 1 is equals to 0. Okay. For getting del t del x, you want this term to be 0. Ti need to be removed. So we say that C naught C1 such a way that they add to 0. Okay. Now from the for this del t del x, from the first term we have C1 plus C minus 1 equals to 0. Okay. Now if you see this equation, in this equation A, how many unknowns are there? Okay. So in equation A, number of unknowns are 3. Okay. That is nothing but C naught, C1 and C minus 1. And we have two equations now, 1 and 2, equation 1 and 2. And we have equations 1 and 2. Therefore, we need For getting solution, we need one more equation. And that one more equation should come through this. Here, we'll have to also write the coefficients delta x and del t del x. Here we can write also coefficient ti. If you add this 1, 2, 3, this addition should be 0. This addition should be 0. Okay. And we need one more. So we also wish to make this 0. So that equation will come as delta x square by 2 factorial and c uh, c1. Okay, here one thing is a mistake. This has to be minus because this is minus, so this has to be minus plus and then minus plus minus. So here this is minus and here this is c1 plus c minus 1 equals to 0. So we have this third equation. So solving these three equations, which also means that solving this equation c naught plus c1 plus c minus 1 equals to 0 and c1 minus c minus 1 equals to 0 and c1 plus c minus 1 equals to 0. Solving these three equations, solving these, we get del t del x is equals to c naught t I plus c1 t I plus 1 plus c2 c minus 1 t I minus 1. Okay. Similarly, you can get any expression in this manner. Okay. You can get for del 2 t, del x2. You can take c naught, c1 like this and try to obtain what are c naught, c1 and c minus 1 and get the expression. So similarly, similar approach can be adopted for higher orders, higher order terms. Okay. Example this. Okay. So let us see. Let us take one example. Now that is a general approach, but we'll adopt a specific approach. Now I want a CD expression, central difference expression for del t del x. Okay, del t del xi with delta x square with order of accuracy delta x square. Now in this case, I'm adopting two approaches. Okay, one approach I will do it in left and another approach I will do it in, or I will say without this. So then I will make one conclusion out of it. So for central difference, in x direction, we consider these points and these points. So this is I minus 1, I plus 1. Okay. Now this is like a one dimension, okay, maybe a thin plate or like that. And we are taking the discrete points of that plate. Okay, you understand this. Many times students do not understand this I plus 1, what, why you are doing and what. And they are at distance, say this is beta delta x and delta x. So I minus 1 is a different delta x and I plus 1 is a different delta x. Now, what do we do is we find out expression from Taylor series for Ti plus 1, okay, that we get Ti plus beta delta x Okay, now what we wish to do, we wish to calculate for this one, del t del x. So we wish to delete this, no, Ti. That is the one thing we can do. Okay, so if you delete this, what we can do is Ti plus 1, Ti plus 1 minus Ti minus 1. Okay, this will give you, this term will go out. So this 1 Ti will become 0. So Ti will go out and this will beta delta x minus delta x. So beta delta x minus, so beta minus 1 delta x del t del x, and we have subtracted. So we have subtracted. So it should be a plus. So this plus beta delta x. So beta also minus 1 beta square minus 1 delta x square divided by 2 factorial delta 2 del x2, and this plus minus this will also become plus, something like. Okay, now if you divide this expression by delta x, divide this expression by delta x, you will get rid of this delta x. You will also get rid of 1 delta x, and here you will get some order of delta x square. Okay. Now what we got is the first leading term. Now it is order of delta x. You see, once you divided it, it is order of delta x, and then you have order of delta x square. But it also depends upon this beta. And this expression del t del x is equals to Ti plus 1 minus Ti minus 1 divided by beta plus 1 delta x plus 1 delta x minus beta square minus 1 delta x 2 factorial del 2t del x2 plus order of delta x square. Now this order of this scheme, order of error of this scheme depends on beta. So say beta is equals to 1, in that case this terms goes off and you get a second order accuracy. Okay. Beta is equals to 1, in that case you get this. If beta is not 1, then you get different accuracy. Okay. So we get accuracy like order of delta x, but we do not wish to add this. Okay. So now another expression, now I want to get rid of this delta x. I want delta x square, and without taking beta is equals to 1, I just want to have a beta there. But I want also order of error accuracy delta x square. So what I'll do? So we can play with these equations, this equation number 1 and equation number 2, such a way that we get rid of this delta 2t del x square, this term. How we can get rid of? So suppose I multiply second equation, equation 2 by beta square. Okay. Then and subtract from equation 1. Then we can get rid of this, isn't it? So we'll do that. So we will write it again, ti plus 1 ti plus beta delta x del
Sir,
t del x square. Huh?
sir, in the previous step, dou t by dou x, there how we are getting that beta plus 1 in the denominator, sir?
We are subtracting this, right?
Yes, sir.
We are subtracting equation 1 and 2. So here beta delta x minus minus is plus. So beta plus 1 delta x, isn't it?
Yes, sir. But since we have that plus beta square minus 1 into delta x by 2 factorial
Where,
term,
where,
sir.
where, where?
The second line, sir. That third
Here,
line, third line, third line.
third line.
Yes, sir. Here we have summation of other terms also, no, sir.
Summation of other terms also. So that is what a summation of this term I have added here. Beta delta x square minus delta x square, isn't it?
Okay, sir.
So that delta x square is here, and I have divided this whole term by delta x. So delta x gone here, one delta x gone here, and one delta x gone here. Otherwise, this should have been delta x square, delta x cube, and here delta x should be there, and this delta x should be removed.
Okay, sir. Sir, and the fourth step, sir.
Fourth step is this I have taken left side, and this I have taken right side. Okay.
Oh, okay, sir. Okay.
Okay. So this del t del x, now I have taken beta plus 1 here also. So here you'll have to have a beta plus 1. Yeah.
Yes, sir. That's what I
This
have.
is okay.
Yeah.
So it depends upon beta. Okay. Here beta delta x, beta square delta x square 2 factorial and del 2t del x2 plus beta cube delta x cube factorial. Okay. And this we are multiplying by beta square. So beta square ti minus 1 is equals to beta square ti plus minus beta square delta x delta t delta x plus beta square delta x square 2 factorial delta 2 delta x square plus minus beta square delta x cube 3 factorial delta 3t delta x cube. Okay. Now if you subtract this ti plus 1 minus beta square ti minus 1, then this will be equals to this will be equals to 1 minus beta square ti uh, plus beta square delta x del t del x, and this term second term goes out, so we have beta cube plus beta square delta x cube 3 factorial delta x3. So what do you see here? If you get this expression dt dx, this will be equals to ti plus 1 minus beta square ti minus 1 and minus 1 minus beta square ti divided by beta plus beta square delta x, and we will have this order of term beta cube plus beta square divided by beta plus beta square, and we have delta x square 3 factorial and del 3 del x3. So this expression has an order of accuracy delta x square. Here order of accuracy is delta x if you take only 2 points, I plus 1 and I. If you take only 2 points, this and this, then you get delta x with this with the choice of beta. Beta is greater than suppose 1. But if you take 3 points, including this point as well as this point and this point for calculating this, then you get order of accuracy 2. Okay. So how many points? How many number of points you require? Suppose you take number of points 2, number of points 2 means if you see the power order of derivative, not power, order of derivative is 1. Okay. And also if you look at the order of accuracy plus order of accuracy, that is also order of accuracy 1, then in that case number of 2 points. Now come to this case, number of points, this case number of points 3, order of the derivative 1, order of accuracy 2. Okay. So suppose you have a derivative like del 2 t del x2 and you want order of accuracy and we want order of accuracy delta x square, then we need at least 4 points. Okay, at least 4 points. In that case, the fourth point can be repetitive also. Okay. So 4 point values we need. So for this expression, del t2 del x square, you have already seen. Now say similarly for del 3 t del x3 with order of accuracy delta x square, number of points or nodes, number of points or nodes required is equals to 3 plus 2, 5. 5 points, 5 nodes information is required. Okay. So in general, if now no information is given and you want to derive your own expression, then in that case you can follow this general approach. Okay. Okay, so you got this. How many number of points you have to take? That depends upon. So I'll just write number of nodes to be considered in deriving finite difference expression for del n phi del x n we with excuse me, with order of accuracy m is n plus m. I mean r. Okay. Now suppose I want forward difference expression, okay, FD expression, not finite difference, this is forward difference, but finite forward difference, expression for del t del x say I with order of accuracy delta x square. Okay, this is forward difference. So in forward difference, suppose this is x direction or x domain. In that case, you discretize this domain and you have these points. So I write any one point as I, and now as per the above rule, I want order of accuracy 2 and my order of the PD is 1. So I need at least 3 points around this I. So I need 3 points. So in forward difference, we always take forward points. So I need to take forward points like I plus 1 and I plus 2. Okay. So we take these 3 points. Now with these 3 points, we want to get a formula which will be accurate in terms of in this order of accuracy. So what do we do? Again, we go for a Taylor series. So we write Taylor series for Ti plus 1 and Ti plus 2. So Ti plus 1. So now this is all about mathematics. So there is nothing much in it. This goes like much more about mathematics. But again we'll write Ti plus 1, Ti plus delta x and Ti plus 2 Ti. So we have to consider these also. Let us say they are delta x and delta x, same delta x. That is easy. Otherwise, that beta and non-uniform grid, little complication. So this is twice delta x. Okay. So we would like to get rid of this term. So what do we do? What should we do? What should we do?
Multiply equation 1 with 2, sir.
Multiply equation 1 with 2. So what we'll do is we'll do equation 2 minus twice of equation 1. So that will give us Ti plus 2 minus twice Ti plus 1 will be equals to our minus Ti plus that will for this order of accuracy delta x square will not have to do this. Okay, that is for getting delta to this derivative. Okay, so since we have written, we'll just reverse this and we'll say that we want order of accuracy 1 and power is 2. Okay, 2 plus 1 again 3. So we'll go like this. So this expression goes like delta x square, I mean twice delta x square minus delta x square del 2t del x2 plus order delta x cube. And here you can, so this is minus Ti plus delta
Sir,
x
4 del
square.
x square minus 2 del x square, right?
Mm-hmm.
4 del x square minus 2 del x square, right?
4.
In above step.
So this will be 2. So this 2 factorial is there.
Okay. Yes.
So plus order of delta x cube. So this will get it like minus ti plus 2 plus 2ti plus 1 minus ti plus ti. This is minus, right? We are taking this side, and this is minus, and we are dividing it by delta x square also. Plus order delta x square. And by simplification, we can write this delta x square ti plus 2 minus 2 ti plus 1 ti delta x square order delta x square divided delta x. So this will be second order expression forward difference for forward difference. Similarly, you can get an expression for backward difference also. While taking backward difference, uh, for backward difference, del 2t del x2 with order delta x, we have to take the ith point and all previous points, I minus 1 and I minus 2. So we are taking I minus 1 and I minus 2 because 2 plus 1, 3. So we are taking these 3 points. Okay, like this. So you can do this as a homework and obtain an expression for this backward difference.
Sir,
Hmm.
sir, suppose if we want to do that order of difference is delta x square means we have to extend that term, sir.
Excuse me, I did not listen you.
In that homework now you
Ah,
have told, no, sir.
ah,
Your
ah,
order of accuracy is delta x, sir.
delta x.
So if it is delta x square or x cube, in the expression above,
Then
we
you
have
have
to
to then
expand.
suppose this is you have del 2t and del x2 with order of accuracy delta x square. First thing is how many number of points you need? 4 points. Okay.
Okay.
So you need I plus I minus 1, I minus 2, or maybe I minus 3 also along with I.
Okay. Okay.
Okay. So you may need these points 1, 2, 3, 4 points. So your expression will be with this, and it will have a form like this. It will have a form like C naught Ti plus C minus 1 Ti minus 1 plus C minus 2 Ti minus 2 plus C minus 3 Ti minus 3. This is also of that form. If you see, this Ti plus 2 delta x square is nothing but a constant, some coefficient, isn't it? it has a coefficient, it has a ti plus 2 has a coefficient 1 by delta x square. That I can write as C2 ti plus 2. Now here I can write plus and coefficient that has C1, which will be minus 2 delta x square. C1 is equal to minus 2 delta x square, ti plus 1. And this I can write 1 by delta x square as C naught ti. So we can write and this I can write plus or whatever minus order delta x square. Rest of the terms of order delta x. So we can write like this. Okay. That is what this general form we were talking about. What will be C naught, C minus 1, C minus 2? That will you get after you solve these equations. These equations with these equations. After you solve these simultaneous equations 1 and 2, like that you will need more equations. It depends upon the number of unknowns are considered. You got this? Okay.
Yes, sir.
Yeah. Um, you can get the answers in the textbook for del 2t or with order this. There are many expressions given as a table. Okay. Um, it is just a mathematical exercise then. Then how to multiply this? You might have to multiply by some 3 or 4 like that. Or then you do like this C1, C naught, C minus 1, C minus 2 like that. The method we have discussed here. And then once you get this coefficient, you solve for this, you will get coefficients. Okay, C naught, C1, they will be either minus, plus like that. So say for example, for this case, you will get this coefficient in this manner. C2, you will get 1 divided by delta x square. C naught also you will get as 1 divided by delta x square, and C1 will be minus 2 divided by delta x square. Okay. You can try for this equation also. Rather than solving like this or saying like that equation 2 minus something like this, you can straightforwardly go and do use that procedure and get this. While doing calculation, be careful about this. Okay, while substitution, you might uh, substitute plus minus and then you might uh, come to some wrong answer. Okay, so okay, now with this, say for example, you have this forward difference expression, backward difference expression, and central difference expression. Say for del t del x, we got. Now say for del 2 del x 2. Okay, along with order of accuracy delta x, or say delta x square, or any order, and any order of PD of any order and order of accuracy of any order. Now, which one to use? Which one? Which out of FD, PD, CD is to use? Any question? In first case, when you started, we said that FD, forward difference, is order of accuracy delta x, isn't it? BD also, we said that order of accuracy delta x. But central difference expression is order of delta x square. So we are tempted to say that central difference is good and we may go for delta x square. But even FD for the same, this delta x square for del t by del x, first order term. Same del t by del x with order of accuracy, we can now see, we have seen that we can get delta x square. Order of delta x square we can get, isn't it? Same we can get delta x square. Now which one to use? Now for this, which one to use? Even in general also, which one to use? Which out of forward difference, backward difference CD is to use? Okay. Now it depends upon it depends upon the uh, node under consideration. Node number, node number one, the node under consideration. Number two, the available information. Available information. Okay. So suppose we have this domain and we have discretized this domain into these many points, and this is, say for example, a fin problem. Suppose this is a fin. So this is a fin problem. Now this is a 1D problem we have considered, and we have divided this into number of nodes. This is the first node, second node, third node, and fourth node. And here there is a boundary condition. This is a boundary, okay, BC2, and this is also BC, boundary condition 1. Now suppose my point under consideration is BC2, this point. This is my ith point, suppose. This is my point under consideration. Now for I, if I want derivative del t del x I, for example, then del t del x has to be used either using forward difference or backward difference or central difference. Which one will you use? That is the question now. Actually, this question is this.
Backward difference.
Backward difference, because we will use backward difference. This one will use, not this and not this. Because for this point, we have only information available is I minus 1. Now suppose I take another, I change now I. Now my I under consideration is this BC. So this is BC2. So BC1 for I, and I want again to calculate del t del x I. Which one will you use? Whether you will use forward difference, backward difference, or central difference. Which one will
Forward
use?
difference.
Forward difference, right. This is not and this is not, because when you go for forward, my information available is I plus 1. This is available node or information. There is no other node for that. So you see, now suppose I am having third condition. Now I want to take this point as ith point, this point as ith point. This is my ith point. And I want to, so for this I, I want to calculate del t del x again, say for example. Then what do I can use? Is shall you use FD? Shall you use BD? Or shall you use CD? Which one I should use?
CD, sir.
Why? Okay. All are possible. All are possible. But suppose I am asking for higher order accurate, then I may say that CD. But again, I can get FD expression and BD expression of delta x square, isn't it? This one, these expressions I can get, isn't it? And again, I can use any of this, isn't it? Because for I point, I have I plus 1 information as well as I minus 1 information is also available. So either you can take backward difference, either you can take forward difference, or you can take central difference. Okay. So this is the first, gauge when to use which method. Also, we'll see in next when we'll talk about these methods, we'll see why CD is not good, where FD and BD are good schemes for calculating such a kind of derivatives. That depends upon that depends upon the nature of the PD. If it is a non-linear kind of PD, then in such cases, if there is a convection term, then to discretize a convection term of this type U del T del X, central difference schemes are having some problem. So what are those problems? We'll see as the properties of the numerical methods. Those can be studied as a properties of the numerical methods. We'll talk about those properties later. Okay. But you understand when to use FD, VD, CD and this thing. Okay. Now there is another method of deriving these PDs that is called as polynomial method. Okay, finite difference expression using polynomials. Finite difference expressions using polynomials. Okay, so say we have a polynomial a naught plus a1 x plus a2 x square. So this is second order. You can take any order of polynomial and it depends upon the, suppose I have a second order polynomial, then I can have del phi del x first order derivative, which will be nothing but equals to a1 plus twice a2 x. I can have second order derivative del phi del x2 is equals to twice a2, isn't it? So if you want finite difference expression for del phi by del x or del 2 phi by del x2, you should have a naught a1 x plus a2 x square. Suppose you want del 3 phi by del x cube, del 3 phi del x cube. Now you do not have any term, so basically you will have to use phi is equals to a naught plus a1 x plus a2 You understand this, okay? Then only this derivative is possible. Okay. So you just remember this in case you wish for say third order. But we'll see how to get del phi by del x or say del 2 phi by del x2 using this polynomial expression. Now these polynomial expressions, since now we have three constants, essentially we'll take some 3 points. So suppose we are starting, these are nodes, okay, these are again nodes. So this is my starting node. I take another node and one more another node, which having a distance delta x, same delta x. You can vary beta delta x and something like that, and then you can get expression of that. But easy is this. This is the easy one. So let us see with this. So at this is all x. So this is, you can say this is x is equals to 0, and the second is x is equals to delta x, and third one is x is equals to twice delta x. Okay. So you can write this phi for x is equals to 0. So for x is equals to 0, phi, you can write phi I. So this is my ith point, I point. This is I plus 1 point, and this is I plus 2 point. And we are willing to get forward difference, forward points. We are taking forward points. Okay. So we'll get a forward difference expression for this del phi by del x. So it depends upon what points you are considering. So now in this case, we take this point. So we can take I minus 1, I minus 2 also. That is also possible. In that case, you will go in a reverse direction. In the delta x, that sense. Okay, phi at x is equals to 0, phi is equals to, means phi I. Phi is nothing but phi I now. Here phi at ith point, phi I is equals to a naught, and then at x is equals to uh, x is equals to x plus delta x. This is x plus delta x, and x plus 2 delta x. This is x plus 2 delta x. Here phi I plus 1 will be equals to a naught plus a1 a1, and what is our x? X is delta x. At x is equals to delta x, you have delta x. So a1 delta x plus a2 delta x square. At x is equals to twice delta x, phi I plus 2 will be equals to a naught plus a1 twice delta x plus a2 twice delta x square. Okay. Now you have these three equations and three unknowns. Okay, you have these equations 3, 1, 2, 3, and 3. You have to solve 1, 2, and 3 for A0, A1 and A2. So from equation 1, we get A0 is equals to phi I, and you do this procedure and you find that phi 1, you have to do some manipulation here. You want A1, so A1 will be, after doing some manipulation, minus phi I plus 2 minus of this plus 4 times I plus 1 of this and minus twice phi I divided by twice delta x. This will be your A1. And A2, from this again you will obtain as something like I plus 2 minus twice phi. You do this at your home and check. Okay. So you have to essentially get this constant coefficients A0, A1, A2. Now you got this. Okay. So what is the derivative del phi by del x? Del phi by del x is basically A1 plus twice A2x. A1 plus twice A2x. Okay. So you substitute this one uh, to find del phi by del x at I. And at I, what is the value of x? Del phi by del x, A1 plus twice A2, x is 0, isn't it? At I is equals to I is ith point, x is a starting point. So this is nothing but equals to A1. Now A1 is itself this, so this will be this 4, 5, 6. A1 is equals to this one minus 5 I plus 2 plus 4 5 I plus 1 minus 3 phi I divided by twice delta x. And del 2 phi by del x2, that del 2 phi by del x2 is itself twice A2. So derivative of this, so essentially this will be twice of this. So twice of this is that delta x square goes out. So you can write phi I plus 2 minus twice phi I plus 1 plus phi I divided by delta x square. Okay. So this is the way you have to get the derivations from the polynomial. Now here you see this polynomial method is little laborious. Number one, here comes the labor to find a, b, c. This is one point. Okay. Now second point is, when I derived this del phi by del x, what is my order of accuracy? Order of accuracy, that is a question. What is my order of accuracy of this discretization? It is not visible. Okay, this is a number one area, this is a number two. So these polynomial methods are generally not taken. Okay. Many times when you take Taylor series, some people will say, oh, why you haven't taken polynomial? It's like that. Maybe so he doesn't know polynomial, so that is why he hasn't taken. But it is not like that. Okay, it is not important. Uh, just to make it complete, I'm just taking this. So number one, polynomial method. Number one point is polynomial method is cumbersome. It cumbersome. Second thing is we cannot we cannot estimate order of accuracy involved in the obtained finite difference expression as we did, as we could get using Taylor series expansion. Okay. So that is the beauty of this Taylor series expansion. So most of the time Taylor series expansion will be shown to derive these finite difference expressions. So that is the reason we'll mostly, but as an exercise or as a homework, you should try. Um, you may be asked to derive some derivatives using these polynomials. Um, and so practice this. Practice how to get this A naught, A1, A2 from this three equation. Here little cumbersome process. It needs little concentration. Then you can get that answer. And also you will have to be very judicious in terms of taking these points. If it is asked forward difference, then you will take forward difference. If it is asked backward difference, then you will take backward points. And if it is asked, central difference, then you will take left as well as right points. Okay. So that is for today. So I stop the class here.